The Doppler effect. This is a very useful and even pervasive tool in physics. It's used throughout physics, not just in the study of waves in acoustics, but also in things like astrophysics. We all have experienced this phenomenon, whether we're conscious of it or not, on a daily basis, perhaps. When you hear a siren whiz by, like an ambo or a cop car or a fire truck, that's the Doppler effect. The Doppler effect was first discovered by the Austrian mathematician Christian Doppler in the 1840s. And he actually originally was studying stars, binary stars, so two stars that orbit a common center of mass. And he was studying the light coming out of these stars, and he showed that the light from these binary stars is shifted in color as the stars orbit each other. And this shift is caused by the relative motion of the stars. Very powerful, can be used to determine things like the time it takes for them to orbit and how fast they're moving. The Doppler effect is represented using a formula. Here it is. Here it is in all its glory. Now, don't get intimidated by this. It's not actually not that scary. It's actually quite simple, and I'll show you how it's that simple. Suppose you have a fire truck. It's got a siren moving along the road. It's moving towards the right here, in this case, and there's someone standing alongside the road watching the fire truck. Suppose they're walking towards the fire truck, and the fire truck is giving off sound. The siren is going off. Now, sound from the fire truck, because the fire truck's moving to the right, let's call this the velocity of the source, V sub source. The velocity, the speed of the truck in a particular direction is given by V sub source. It's moving to the right. And suppose the person is moving to the left at a velocity V sub observer. The observer is just watching the fire truck. He's moving to the left and the fire truck's moving towards the right. And the fire truck is giving off a sound. And the sound from the siren travels like this. Let me show you. Travels in, on pen and paper, so using this diagram, you can see that I'm restricted to 2 dimensions. Left, right, up and down. But in reality, in practice, sound travels in concentric spheres in 3 dimensions. So just picture sound emanating from the siren in all directions, like so. Let me draw it a bit better. Now, because the fire truck's moving towards the person, the waves coming from the siren get compressed. The reason why they get compressed is because of the motion of the fire truck relative to the observer. That's why you hear a higher pitch, a higher sound coming from the fire truck when it's approaching you. But when the fire truck's moving away from you, suppose you're now standing at the back here, when it's moving away from you, the sound spreads out. The waves are no longer bunched up. The wavelength, I should say, of the waves gets bigger and bigger. That's why the sound gets less and less when it moves away. Let's call the sound coming from the siren V sub wave. The velocity of the wave, the sound wave, coming out of the siren is V sub wave. And suppose the observer on the ground can measure the frequency of the sound coming from the fire truck, F dashed or F prime. In physics, 2 quantities like in physics, quantities, suppose there's, so F prime, that dash there is a prime, and the fire truck, let's say there's someone in the fire truck and they see a frequency F. So they see that the frequency of the sound coming out of the siren is F. The observer on the ground will measure a sound frequency F prime or F dashed. In physics, we use prime to represent different quantities. If it's the same quantity but experienced by different observers. So suppose there's, I don't know, temperature. Someone's in a room. Actually, that's not a bad analogy. Okay, never mind. F and F, two frequencies. It's really hard to word. Someone watching the fire truck approaching, someone hearing the siren will measure the frequency of the sound wave as F prime. Someone in the fire truck will measure frequency F. They can, it's fine. You can interchange these. It's fine, but typically in the Doppler effect, this is the formula. That's how it works. F prime is the frequency measured by the observer, and F is the frequency that's moving with the source of waves. In this case, the fire truck. So that's it. That's the formula. Now, V wave typically will be 340 meters per second. It's a number. It's a constant. This is usually given in a data sheet in an exam. This will be assumed knowledge in a question. You'll have to know this just based on common sense and logic. So if a question presents itself as follows, fire truck and person, you know what, let's say F is, you know what V observer is, V source is, but you don't know what V wave is, you'd have to assume that it's the speed of sound. Okay, sound moves at 340 meters per second in air, I should say. That's given on the data sheet. Let's do an example. Let me illustrate this using an example to make more sense. So e.g., actually we use the same scenario above. Okay, suppose the siren has a frequency 800 hertz. And suppose the fire truck is traveling at 25 meters per second. And the person is moving towards the fire truck at a speed of, let's say, 15 meters per second. Let's say they're really running, this person. What's the frequency of the sound heard according to the person? So this guy will be running really fast, 15 meters per second. So with this, we need the Doppler effect formula. F prime is F V wave minus or plus V observer divided by V wave minus V source. Okay, so what do we have to work with now? F prime, if you recall, is the frequency of the person who's observing the source of waves approaching or moving away from them. So that's this. Okay, recognize that. F is the frequency of the siren. That's given there, 800 hertz. Velocity of the wave, here you have to assume the speed of sound, 340 meters per second. Velocity of the observer, that's the person who's moving, 15 meters per second. Velocity of the source, that's the speed of the fire truck, 25 meters per second. So that's it. That's really the hard bit. The hard bit's just trying to recognize, identify where things are. Easy bit's just sub and solve. Sub in your numbers and solve. So F prime is F is 800. V of the wave, velocity of the wave is 340. Plus velocity of the observer is 15 meters per second divided by velocity of the wave, once again 340. Velocity of the source is 25 meters per second minus 25, and that is it. The rest is just plug and play, put it into your calculator, and you should get an answer of 902 hertz. And I tell my students, always do a sanity check. So why does this make sense? Well, if you think about it, the person on the ground watching the fire truck approach them will experience a higher frequency, will measure a higher frequency than the siren, the person in the fire truck themselves. Why is that? Well, because remember, the waves get compressed. If the waves get compressed, the frequency goes higher. So seeing this phenomenon like this, that indicates that the frequency is getting shorter. Whereas at the back of the fire truck, waves are moving away from the fire truck and away from the observer. Frequency gets stretched out, it gets less. So that's, if you get a higher number for the frequency for someone who's observing the source of waves approaching them, it's higher, it makes sense logically if you think about it. Okay, more compressions, closer peaks, higher frequency. Okay, the wavelength is shorter, the distance between two peaks, two crests. Shorter wavelength means higher frequency, more peaks. Now I should emphasize with this formula that you can have a minus in the numerator and a plus in the denominator. Or before that, I should just say, just briefly, why would it be plus and why would it be minus? Well, if you think about it, think of the top, the numerator, as being, so the person who's walking towards the source of waves, the velocity of the wave and the velocity of the observer add up. Okay, because the person's walking towards the waves coming towards them. So it adds up like that. Think of the fire truck. Think of the waves coming out of the fire truck, the sound waves. They're moving away from the fire truck. So that's why you minus here, down here. Okay, velocity of the wave minus velocity of the source. Now you can have a situation where they're traveling in opposite directions. So it's important to emphasize in this formula. I said this to my students the other day. This formula applies to two objects moving towards each other. If they're moving in opposite directions, you put a minus in the numerator and a plus in the denominator. And a sanity check, if you think about it, the sound waves are moving away from the observer if they're moving in opposite directions for the numerator. For the denominator, the waves are catching back up to the source of waves. And that's the Doppler effect. Now, I should also emphasize that this formula, if there's no relative motion between the two observers, this formula will not work. Okay, you need to have relative motion. You need to have movement between two observers. Or at least if one of them is stationary, then that term is zero. Suppose the source of waves is stationary, this term vanishes to zero, for example. But suppose the velocity of the observer, you can try this as an activity, and the velocity of the source is the exact same number, let's say 100 each. That divided by that cancels out, and you're left with velocity of the wave versus velocity of the wave. That's 340 divided by 340, that's 1. So you're left with this, the frequency observed, equaling the frequency that's coming out of, that's due to the moving object. So there's not going to be any shift or change in frequency if both objects are moving at the same speed. Try that as an activity and see how you go with it. But it's just a nice, neat formula. It shows you just what happens when there's motion between two objects and there's a source of waves coming out of one of the objects.